Welcome to my channel. This video I am going to discuss about basis and dimension. Let us get into the video. So I have given the basis definition. The definition goes as such: a subset B of a vector space V is said to be the basis, that is L of B equal to V for V if the number one condition is B is linearly independent and number two, B spans V. B spans V means B must generate V. We know that B is going to be a subset which is for a vector space V, and when it will become a basis, in the sense it must satisfy the condition B must be linearly independent and B spans V, then it is going to be the basis for the given vector space V. Let us get into the example. So consider the set V is equal to V2 and consider the subset B is equal to 1 0 0 1. Now we need to show that B is linearly independent. So for B is linearly independent, for A1 1, 0 plus A2 0 1, I can write this as A1 equal to 0 0. That's the equation we know that. Then that is equal to A1 A2 0 0, and that is equal to A1 equal to 0 and A2 equal to 0. That means it has a trivial solution and hence B is linearly independent. Now the second condition is B must spans V, that is it has to generate V. So for B spans V, let me take a vector, any vector alpha 1 and alpha 2 of V2 can be expressed as the linear combination of B1 for alpha 1 alpha 2. I can write it as it is equal to alpha 1 into 1 0 plus alpha 2 into 0 1. That means if I choose any vector from V2, that is alpha 1, alpha 2, and I am able to express this vector in terms of the given subset, which is going to be 1 0 and 0 1. So hence any vector can be expressed as the linear combination of the given subset B, that is L of B is equal to V. Therefore B spans V. So by the definition, B is going to be the basis for V2. Now let us see the note. It may be seen that B1 is 1 1 and 1 minus 1. That means I am taking another subset of the vector space V2, and that is taken as 1 1 and 1 minus 1. Now I am going to show that this also can act as a basis of V2. So the first condition is it should be linearly independent. For linearly independent, I have taken that as A1 into 1 1 plus A2 into 1 minus 1 is equal to 0 0. So if I take this as an equation, it becomes A1 plus A2 equal to 0 and A1 minus A2 equal to 0. So by solving you get A1 is 0 and A2 is equal to 0. So it has a trivial solution and hence B1 is going to be linearly independent. Now the second condition, it has to spans V. So for that vector alpha 1 alpha 2 belongs to V2, I am able to write this vector as alpha 1 alpha 2 is equal to alpha 1 plus alpha 2 by 2 into 1 1 plus alpha 1 minus alpha 2 by 2 into 1 minus 1. So when you solve this, see you have to multiply with the 1 and this 1, and similarly here when you solve this you will get alpha 1, and when you solve these two you will be getting that is going to be alpha 2. So I am able to express the vector alpha 1 alpha 2 which belongs to V2, that's an element in V2, I am able to express in terms of the given subset 1 1 and minus 1, and hence this B1 also spans V. So it is linearly independent and it spans V, so it is going to be the basis of V2. So from this we can conclude that the basis for a vector space need not be unique. So not necessarily we need to have only one basis in a vector space. It is possible to have more than one basis. That is why I have given this example. Thanks for watching. See you in the next video.